Metals bond to non-metals through ionic bonding. A group 1 metal needs to lose an electron, while a group 7 atom needs to gain one. For example, a lithium atom donates or loans its outer electron to the chlorine. We can draw a dot and cross diagram to show where the electrons end up. You can choose which one belongs to which. We only need to draw the outer shell for each. Don't forget to put brackets and the charge of the ions when it comes to ionic bonding. The charges of all ions in an ionic compound must add up to 0, so Li plus and Cl minus is all good. So this is the chemical formula for it. Same with beryllium oxide, Be2 plus and O2 minus. Beryllium chloride, on the other hand, well, the beryllium needs to lose 2 electrons while a chlorine only needs 1. So that means there must be 2 chlorines or chloride ions for every beryllium. So Be2 plus and 2 lots of Cl minus adds up to 0. So that means the chemical formula is BeCl2. Sorted. Non-metals bond to each other with covalent bonding to form molecules. They do this by sharing electrons to gain full outer shells. For example, chlorine gas is Cl2. Each chlorine atom shares an electron with the other. Here's the dot and cross diagram. We can also draw the structural formula for molecules with just symbols and lines. Each oxygen needs 2 extra electrons, so O2 is a result of each oxygen atom sharing 2 electrons each. As such, this is a double covalent bond. In covalent bonding, the number of electrons an atom needs is the same as the number of bonds it must make. Hydrogen can only ever make 1 bond, carbon makes 4 bonds, etc. Here's a few more. These above are what we call simple molecular or simple covalent structures, individual molecules that can all mix together. These have relatively low boiling points as there are only weak intermolecular forces between them that need to be overcome with heating. Metal atoms bond to each other through metallic bonding. Essentially a lattice or grid of ions is formed with a sea of delocalized electrons around them. Delocalized just means they're not exactly on the atom. As these electrons are free to move, metals make good conductors of electricity and heat.
Intermolecular forces are interactions between molecules in a covalently bonded structure. And these are broken apart when the structure changes phase, so for example from a liquid into a gas, whereas the interatomic forces remain intact in a phase change. And intermolecular forces are called van der Waals forces, or non-covalent interactions, as they're generally much weaker than forces in solid structures. So these are grouped into interactions between non-polar molecules, non-polar and polar molecules, polar and polar molecules, and ions and polar molecules. So they get stronger as we move from left to right. And hydrogen bonding is a special type of dipole-dipole interaction, which is stronger than regular dipole-dipole interactions.
Dipole-dipole interactions which involve permanent dipoles due to the differences in electronegativity between atoms in the molecule. Hydrogen bonding is a specific type of dipole-dipole interaction where we have a hydrogen bonded to an oxygen, nitrogen, or fluorine atom. Because of the high electronegativities of these atoms, these bonds have particularly large dipoles, where the bonding electrons are pulled away from the hydrogen. Moreover, pulling the electrons away from the hydrogen atom exposes the hydrogen's nucleus, which is just a single proton. By comparison, pulling the electrons away from a carbon atom exposes the core electrons of the carbon atom. So, with hydrogen, this results in very strong dipole-dipole interactions that we call hydrogen bonding. These are the strongest type of intermolecular force that don't involve ions.